What happens if a black hole consumes a planet? Black holes are among the most mysterious and fascinating objects in the universe. These regions of space, where gravity is so intense that not even light can escape, captivate the imagination of both scientists and the general public. One particularly intriguing question is, what happens if a black hole consumes a planet? To answer this, we need to delve into the nature of black holes, how they interact with their surroundings, and the complex processes that occur when matter, such as a planet, falls into them. The anatomy of a black hole. Before understanding the fate of a planet consumed by a black hole, it's important to first explore what a black hole is. At its core, a black hole is a region in space where matter has been compressed into an incredibly small area, resulting in an immense gravitational pull. This compression happens when a massive star collapses under its own gravity at the end of its life cycle, forming what's known as a stellar black hole. There are also supermassive black holes, which exist at the centers of galaxies, and intermediate mass black holes, whose origins remain an ongoing mystery. The defining feature of a black hole is its event horizon. This is the boundary beyond which nothing can escape the gravitational pull, not even light. Once an object crosses the event horizon, it is destined to move toward the singularity, a point of infinite density at the very center of the black hole. Outside of the event horizon, however, the gravitational effects of a black hole extend far into space, influencing nearby objects like stars and planets. Tidal forces and spaghettification. One of the most immediate effects of a black hole on a nearby planet is the immense gravitational pull, which causes tidal forces. These forces arise because the side of the planet closest to the black hole experiences a stronger gravitational attraction than the side facing away. As a result, the planet would begin to stretch and deform as it approaches the black hole. This process is often referred to as spaghettification because it would literally stretch the planet and any objects on it into long, thin strands resembling spaghetti. The extent of spaghettification depends on the size of the black hole. For smaller black holes, the tidal forces near the event horizon are so intense that the planet would be torn apart before even reaching the event horizon. In contrast, for supermassive black holes, which have a much larger event horizon, the tidal forces would be more gradual, allowing the planet to pass through the event horizon largely intact before being shredded apart closer to the singularity. Accretion disk formation. As the planet approaches the black hole, it would not simply disappear immediately. Instead, it would likely become part of an accretion disk, a swirling ring of gas, dust, and other debris that orbits the black hole. When planets, stars, or any other matter fall into a black hole, they don't fall in all at once. Due to the immense gravitational forces, this matter is first broken down into smaller components, gases, dust, and other particles. These particles form the accretion disk, and, as they spiral inward toward the black hole, they generate incredible amounts of heat and radiation, particularly X-rays. The formation of an accretion disk is one of the most energetic processes in the universe. As material spirals closer to the event horizon, it accelerates to nearly the speed of light. The intense friction between the particles in the disk produces vast amounts of radiation, often outshining entire galaxies. If the planet being consumed is large enough, this process could produce a temporary but spectacular flare of X-rays and other electromagnetic radiation, visible to astronomers from far across the universe. What happens inside the event horizon? Once the planet crosses the event horizon, its fate is sealed. From the perspective of an outside observer, it would appear as though the planet slows down and fades from view as it approaches the event horizon due to the effects of time dilation. This is a consequence of Einstein's theory of general relativity, which predicts that time appears to slow down near massive objects like black holes. However, from the planet's own perspective, or from the perspective of an object falling with it, it would continue to move toward the singularity. Inside the event horizon, the planet would be subjected to extreme tidal forces that would compress and stretch it further until it was completely broken down into its constituent atoms and subatomic particles. All this matter would then be pulled inexorably toward the singularity, the point of infinite density at the center of the black hole. At this point, the planet, or what remains of it, becomes part of the black hole's mass, contributing to its growth. Information loss paradox. The process of a planet being consumed by a black hole also raises an important question in modern physics. What happens to the information contained in the planet? According to quantum mechanics, information about the physical state of an object should never be lost, but when a planet or any other object falls into a black hole, it seems that this information is destroyed once it passes the event horizon. This apparent contradiction is known as the information loss paradox. While classical physics suggests that all matter and information are obliterated upon reaching the singularity, quantum mechanics insists that information must be preserved. This paradox has led to extensive debate and research in theoretical physics. Some theories, such as the idea of holographic principles, suggest that the information about the consumed planet might be encoded on the event horizon itself, preventing its total loss. However, this remains a deeply unresolved issue in modern science. The effects on the planetary system. The consumption of a planet by a black hole would also have far-reaching effects on any nearby planetary system. Planets that are too far from the black hole to be directly consumed would still be significantly affected by the black hole's immense gravitational pull. If the black hole were part of a binary star system, the gravitational disruption caused by the black hole consuming the planet could potentially destabilize the orbits of nearby planets, moons, or other celestial bodies. Moreover, if a planet were large enough, or if the black hole were rapidly consuming matter, the resulting accretion disk and radiation could produce powerful jets of energy known as relativistic jets. These jets, which shoot out from the poles of the black hole at nearly the speed of light, could blast through nearby star systems, potentially disrupting any planets or stars in their path. Conclusion: the ultimate fate. In summary, the consumption of a planet by a black hole is a violent and complex process that involves gravitational tidal forces, accretion disk formation, and the eventual spaghettification of the planet. The planet would first be stretched and torn apart by the black hole's immense gravitational pull, then broken down into smaller components that would form part of the black hole's accretion disk. Finally, the matter would pass through the event horizon and be drawn toward the singularity, where it would be forever lost to the outside universe. The information loss paradox remains an unsolved problem in modern physics, adding an extra layer of mystery to the process. This fascinating and extreme event showcases the immense power of black holes and their ability to consume even planets, leaving nothing but radiation and questions in their wake.